When we talk about deep learning frameworks such as TensorFlow and PyTorch, we often focus on neural networks, optimization, training loops, or GPU acceleration. But beneath all of those abstractions lies a very simple and very powerful idea: everything is built on tensors. If you truly understand tensors, you understand the language these systems speak internally. Neural networks are not magic, they are structured transformations of tensors. At a very basic level, a tensor is a container for numerical data arranged in a structured way. Many people start with the idea that a tensor is just a multidimensional array, and while that is not wrong, it is incomplete. A tensor is not only about shape, it is about how data is organized, how it moves through computational graphs, how it participates in operations, and how it is stored and manipulated efficiently on different hardware architectures. Think first about the simplest case, a single number. In deep learning terminology, even a single number is represented as a tensor. It is sometimes called a zero-dimensional tensor. That might sound overly formal, but it creates a unifying perspective. A scalar, a vector, a matrix, and a multidimensional block of data are all tensors. They differ only in the number of dimensions, not in their conceptual identity. A one-dimensional tensor can be thought of as a vector. It is a sequence of numbers arranged along a single axis. In practical deep learning systems, this might represent a feature vector describing one data sample, or a list of weights associated with a single neuron. A two-dimensional tensor is typically called a matrix. This is what we use to represent batches of data, weight matrices between layers, or tabular datasets. Once we go beyond 2 dimensions, we often stop using traditional linear algebra names and simply refer to them as higher-order tensors. A 3-dimensional tensor might represent a batch of sequences, or a color image with height, width, and channels. A 4-dimensional tensor might represent a batch of images, adding one more axis for batch size. And so on. The key idea is that tensors generalize all of these cases into one consistent abstraction. Frameworks like TensorFlow and PyTorch were designed around this abstraction so that every operation, from the simplest addition to the most complex convolution, can be described as a transformation from one tensor to another tensor. One of the most important properties of a tensor is its shape. The shape tells you how many dimensions the tensor has and how large each dimension is. For example, if you have a tensor representing a batch of 64 color images, each with height 224, width 224, and 3 color channels, the shape might be described as 64 by 224 by 224 by 3. The meaning of each dimension is contextual. One dimension might represent batch size, another spatial height, another spatial width, another channel depth. The framework does not inherently know what these dimensions mean semantically, it only knows how to operate over them mathematically. The semantics are imposed by how you design your model. Another crucial concept is the idea of data type. A tensor is not only defined by its shape but also by the type of numbers it contains. These might be 32-bit floating point numbers, 16-bit floating point numbers for more memory-efficient training, 64-bit floats for higher precision, or integers for indexing and categorical data. Data type affects memory usage, computational speed, and numerical stability. In high-performance training on GPUs or specialized hardware accelerators, the choice of data type can dramatically affect throughput. Under the hood, tensors are stored in contiguous blocks of memory. Their multidimensional structure is mapped onto linear memory using a particular layout strategy. Two common layout strategies are row major and column major ordering. Most deep learning frameworks use row major ordering, but understanding that this mapping exists helps explain performance differences. Access patterns that align with how memory is laid out are faster because they take advantage of caching and hardware prefetching. Poorly aligned memory access can slow down training significantly. Another concept closely related to shape is strides. Strides describe how many memory steps you need to take to move along each dimension of a tensor. When you slice a tensor or create a view into it, you are often not copying the underlying data. Instead, you are creating a new tensor object that points to the same memory but interprets it with different shape and stride information. This makes many operations extremely efficient because they avoid memory duplication. However, it also introduces complexity, modifying one view can affect another view if they share underlying storage. Broadcasting is one of the most powerful and elegant features of tensor-based frameworks. Broadcasting allows operations between tensors of different shapes under certain compatibility rules. For example, if you have a tensor representing a batch of data and another tensor representing a single bias vector, the framework can automatically expand the bias across the batch dimension without explicitly copying it. Broadcasting reduces the need for manual reshaping and tiling, making code more concise and expressive. Conceptually, it works by virtually expanding dimensions of size 1 to match larger dimensions during arithmetic operations. Deep learning frameworks treat tensor operations as first-class citizens. When you add two tensors, multiply them, perform matrix multiplication, apply an activation function, or compute a convolution, you are executing highly optimized tensor operations. The operations are implemented in low-level languages and often call into hardware-accelerated libraries. On GPUs, they are mapped to thousands of parallel threads. The abstraction remains simple, but the execution is massively parallel. An essential idea in frameworks like TensorFlow and PyTorch is automatic differentiation. Tensors in these systems are not just containers of numbers, they can also track how they were produced. In PyTorch, for example, a tensor can have a flag indicating that it requires gradients. When this flag is set, the framework builds a dynamic computational graph as operations are applied. Each operation records how it transforms input tensors into output tensors. During backpropagation, the framework traverses this graph in reverse, computing gradients of a loss value with respect to every parameter tensor. This mechanism relies entirely on tensor operations. Gradients themselves are tensors with the same shape as the parameters they correspond to. The backpropagation algorithm becomes a systematic application of tensor operations following the chain rule, even though we are not expressing it with formal mathematical notation here. The important point is that differentiation is implemented as structured transformations over tensors. In TensorFlow, especially in its earlier versions, computational graphs were defined statically. You describe the entire graph of tensor operations before running it. In more modern usage and in PyTorch, graphs are often dynamic, meaning they are constructed on the fly as code executes. In both cases, the core abstraction remains the tensor. The difference lies in how the sequence of tensor operations is recorded and executed. Another important aspect of tensors is device placement. A tensor can live in CPU memory, GPU memory, or on specialized accelerators such as TPUs. Moving tensors between devices is an explicit operation in many frameworks. If you attempt to perform operations between tensors on different devices, you will get an error. This is because the underlying memory spaces are separate. Understanding device placement is crucial for performance tuning. Data transfers between CPU and GPU are relatively slow compared to computations inside GPU memory, so minimizing these transfers is key to efficient training. Let us consider a simple neural network layer. At its core, it performs a linear transformation followed by a nonlinear activation. The linear transformation can be viewed as a tensor representing input data multiplied by a tensor representing weights, producing another tensor. The activation function then applies an element-wise transformation to that output tensor. Every step is a tensor in, tensor out operation. When you stack layers, you are chaining tensor transformations. When you train the network, you are adjusting weight tensors based on gradient tensors. The entire system is a pipeline of tensor manipulations.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.